The increasing order of the pKa values of the following compounds is which one? First of all, what is the connection between pKa values and these four molecules? We have phenol, paranitrophenol, metanitrophenol and paramethoxyphenol. The connection is acidity. We know that acidity is indirectly proportional to pKa values. So therefore, if the compound is more acidic, then it means that it will have smaller pKa values. More acidic means smaller pKa values. So among these four molecules, which one will be more acidic? Obviously, paranitrophenol will be more acidic because the corresponding conjugate base will be more stable, isn't it? Acidity is directly proportional to stability of conjugate base. Let's write that one also. Acidity is directly proportional to stability of the conjugate base. So therefore, we have to see the resonance structures. If you carefully look at the resonance structures of paranitrophenol, then you can realize that the negative charge is delocalized into the nitro group. That's the main thing here. The negative charge is delocalized all the way to the nitro group. That's why the conjugate base is more stable. On the contrary, if you compare paranitrophenol with metanitrophenol, which one will be more stable? Obviously, paranitrophenol will be more stable because if you look at the resonance structures of metanitrophenol, here the negative charge is not delocalized into the NO2 group. That's the key difference. So we do have a negative charge here because NO2 is a strong electron withdrawing group. It has negative mesomeric effect, but unlike paranitrophenol, here the negative charge is not distributed into the nitro group. That's the key difference. So therefore, compared to metanitrophenol, paranitrophenol is more stable. So therefore, paranitrophenol is more acidic compared to metanitrophenol. So this means B should come first, isn't it? That will have smaller pKa value. After B, C should come. So this means 2 is wrong, 4 is also wrong, isn't it? So now between A and D, which one will be more acidic? Obviously phenol will be more acidic. Why? Let's compare the resonance structures of phenol and paramethoxyphenol. If we look at the paramethoxyphenol, one of the resonance structures will have two negative charges adjacent to each other. So such a resonance structure will be less stable. Even though we have positive mesomeric effect in both the cases, the conjugate base of paramethoxyphenol will be less stable compared to phenol. So therefore, phenol is more acidic. So this means that the pKa value of A will be smaller than D. So therefore, option 1 is correct in this case. The increasing order of the pKb of the following compounds is which one? We have 4 different molecules. All of them are derivatives of thiourea, isn't it? On one side we have phenyl ring, on the other side we have para substituted phenyl ring, and that's where comes the difference. But all of them are derivatives of thiourea. Now what is the connection between pKb values and basicity? We know that basicity is how quickly the electron pair is available for protonation. If a molecule has to be more basic, then it is ready to accept the proton, isn't it? Proton donor is acid, proton acceptor is base. So how quickly it can accept the proton? So this means we have to look at both inductive effect as well as resonance effect or mesomeric effect. In this case, we have lone pairs of electrons on top of nitrogen. On one side we have phenyl ring, so that is not going to make any difference. But the difference that is going to make is because of these groups. So we have fluorine, we have methoxy, we have nitro group, as well as we have a methyl group. Among these, we know that fluorine as well as NO2 are electron withdrawing groups, but NO2 is a strong electron withdrawing group compared to fluorine. On the contrary, methoxy as well as methyl group are electron donating groups, but methoxy is a strong electron donating group compared to methyl. And we know that basicity is inversely proportional to pKb values, which means lower the pKb value, stronger is the base. Lower pKb means stronger base. Why? Because pKb is equal to negative logarithm of Kb. So therefore, when we have lower pKb value, we will have higher Kb value, isn't it? Likewise, when we have higher pKb value, that would be a weaker base. If we are having higher pKb value, then that means that it is a weaker base and lower will be the Kb value. Okay. Now keeping these in mind, we have to solve this problem. Let us first compare between B and C. The reason is we have a powerful electron withdrawing group on one side, that is nitro, and then we have a powerful electron donating group on the other side. So therefore, let's compare between B and C first. So let us look at the resonance structures. In the case of para-methoxy derivative, we would have both negative inductive effect as well as positive mesomeric effect, but it is the positive mesomeric effect that dominates, and consequently it makes the lone pair more available. Lone pair that is there on top of nitrogen, it makes it more available for protonation. So therefore, obviously this is a stronger base, which means B should come first. If B should come first, then 3 is wrong, 4 is also wrong. Next to B, it is mentioned as D. So when we have a methyl group, we would have positive inductive effect, isn't it? And also methyl group can participate in hyperconjugation. So therefore, D is next. And then between C and A, which one will be a weaker base? Obviously C will be a weaker base. Why? Because nitrogen is a strong electron withdrawing group. We would have both negative inductive effect as well as negative mesomeric effect, but it is the negative mesomeric effect that dominates, and due to which the lone pair is less available for protonation. So which means that C should come last. That will have higher pKb value. This means option 2 is correct, option 1 is wrong. When we have fluorine, we would definitely have negative inductive effect. We would also have positive mesomeric effect, but it is the negative inductive effect that would dominate. But compared to NO2 group, fluorine is not a powerful electron withdrawing group compared to NO2. It is an electron withdrawing group, but compared to NO2, it is not a powerful electron withdrawing group. So obviously C should definitely come last, which means that option 2 is the only correct choice here. the number of chiral carbons present in the following molecule given below is how many? The given compound looks like a derivative of quinine, which we use in the treatment of malaria. A carbon atom or a heteroatom connected to 4 different groups is what we call it as chiral. In this case, we are going to look only carbon atoms because they said chiral carbons. Therefore, we don't have to worry about heteroatoms. We follow the elimination method because it is easier. We can eliminate all the methyl groups because methyl group has 3 hydrogens. Therefore, in total it would become 2 different groups, not 4 different groups. Even though the hybridization is sp3, we can still eliminate that. So, this is a methyl group, we can eliminate it. This is a methyl group, and then this is a ethyl group, but if we divide, then we can consider this as a methyl group, and then this one as a methylene group, because we have 2 hydrogens. So, in total it would become 3 different groups, not 4 different groups. So, therefore, all the methylene groups we can eliminate. Methylene, methylene, this is also methylene, and then this is also methylene. And then we can also eliminate all the carbon atoms that are sp2 hybridized. So, if we have a carbon-carbon double bond, we can eliminate. So, this means all these 6 carbon atoms we can eliminate, and then all the carbon atoms that are there in the quinoline ring we can eliminate. Now, let us look at the remaining carbon atoms. Let us mark them. So, 1, 2, 3, 4, 5. These 5 carbon atoms could potentially be chiral. Obviously, this one is chiral because we have a hydrogen, we have an alcohol functional group, we have a methyl group, and then this entire unit can be considered as one unit. So, therefore, it is indeed chiral. And then how about here? We have a hidden hydrogen, and then this is one unit, and then this one is another unit, and then the rest of the thing we can consider it as one unit. So, therefore, this is also indeed chiral. So, here also we have a hidden hydrogen that is connected to a nitrogen, and then CH2 on this side, and then CH on this side. So, therefore, this is also chiral. How about here? We have a hidden hydrogen, and then CH2 here, and then CH on this side, and then again CH2 here. But look at the next carbon. Next carbon here is CH2, but here it is not CH2. It is connected to CH. So, therefore, there is asymmetry. Therefore, this carbon atom is indeed chiral. How about this one? We have a hidden hydrogen, and then we have an ethyl group here, and then CH2, and then here it is CH. So, therefore, this is also indeed chiral. This means the total number of chiral carbon atoms that we have is 5. Therefore, 5 is the correct answer here. Which of the following compounds produces an aptically inactive compound on hydrogenation? We basically adding H2 for each compound, and then we have to figure out which one is optically inactive. So, if we add H2 for 1, then it would become 1, 2, 3, 4, 5, 6, and then we have a methyl group at the 4th position. That means it is still optically active because this is a chiral center, isn't it? We have a propyl group here, we have a ethyl group, we have a methyl group, and then hydrogen. So, therefore, we still have a chiral center. That means it is optically active. Therefore, this is not our correct choice. and then for the second one it would become 1, 2, 3, 4, 5, 6, 7. At 6th position we have a methyl group, and then at 4th position we have methyl group. This means this would still be optically active because we have a chiral center at the 4th position, because we have a propyl chain, and then we have this chain like propyl chain with a methyl group, and then a methyl group, and then a hydrogen. So therefore it would be optically active. Therefore 2 is not our correct choice. And then 3 would become 1, 2, and then a methyl group. Basically we have a isopropyl chain, and then 1, 2, 3, 4. We have a 1, 2, 3. At 3 position we have a methyl group. This means it would still be optically active because we have a isopropyl chain, methyl group, hydrogen, and then a propyl chain. Therefore we have 4 different groups, which means this would be optically active. And then for the 4th one it would be 1, 2, 3, 4, 5, and then at 4th position there is a methyl group, and then at 2nd position also there is a methyl group, and then at 3rd position we have a methyl group. This would become optically inactive, isn't it? Because we have 2 isopropyl groups attached to the same carbon. Therefore in total we have 3 different groups, not 4 different groups, isn't it? We require 4 different groups so that it can become a chiral center, but here we have only 3 different groups. Therefore this is optically inactive after hydrogenation, which means option 4 is the correct choice here. The number of sp2 hybrid orbitals in a molecule of benzene is how many? They are not asking the number of sp2 carbons, they are asking the number of sp2 hybrid orbitals. We know that molecular formula of benzene is C6H6. We can write 2 dominant resonance structures. We also know that in benzene each carbon atom is sp2 hybridized. But the question is, each carbon atom will have how many sp2 hybridized orbitals? Carbon in the ground electronic state, the electronic configuration is 1s2, 2s2, 2p2. In the excited electronic state, the electronic configuration is 1s2, 2s1, 2p3. One electron from 2s would jump to 2p in the excited electronic state, and the atomic orbital of 2s gets mixed up with the 2 of the atomic orbitals of 2p. That is how we form the sp2 hybrid. But we will have 3 equivalent sp2 hybrids, isn't it? So therefore 3 times 6, that is equal to 18 sp2 hybrids is what we will have. So therefore the correct answer is option 3, because one sp2 hybrid will be utilized in making the sigma bond with the hydrogen, and we have 6 CH bonds, and then another sp2 hybridized orbital will be used in making the carbon-carbon sigma bond on one side, and then another one will be used in making another carbon-carbon sigma bond on the other side. And then this electron that is there in the pz orbital, it would be perpendicular to the molecular plane, that would be making the pi bond having a sidewise overlap. That is how we have the delocalization throughout the ring. So all the sp2 hybrids will be utilized for the sigma bonds. But how many sigma bonds we have? We have 6 CH sigma bonds and 6 carbon-carbon sigma bonds. So the total number of sigma bonds in benzene is 12, and we have 3 pi bonds. But for pi bonds we won't be utilizing the sp2 hybridized orbitals. Only for making the sigma bonds we would be using the sp2 hybridized orbitals. We have an organic molecule and we need to find out the IUPAC name. Unfortunately, all the options given here are wrong. I'll tell you why. We have a carboxylic acid functional group and we also have an aldehyde. This is not a keto group. The hydrogen atom here is hidden because we know that aldehyde is a terminal functional group and ketone is not a terminal functional group. So if it comes at the end, you can say for sure that it is a aldehyde and one hydrogen atom is hidden there. Now we also know that carboxylic acid gets the top precedence compared to aldehyde. Therefore, we have to end the name with the oic acid. This means option 1 is wrong, option 2 is also wrong. Let's come to the numbering. So we have to start our numbering from here 1, 2, 3, 4, 5 and then 6. At the 5th position we have an aldehyde, but here it is written that 6 carboxy. If we write 6 carboxy, what would happen? It would create a carboxylic acid functional group at the 6th position. That means it would extend the chain, isn't it? So if we put 6 here and then at the 6th place if we are writing carboxy, then that would extend the chain. So let us look at that structure in option. So if we write 2,5 dimethyl 6 carboxy hex 3 in oic acid, then let's do the numbering 1, 2, 3, 4, 5, 6. You see at the 6th position we are writing a carboxylic acid. So therefore that name is definitely wrong. And by the way, geometrical isomerism is not considered for this example. So in case if I haven't said it, geometrical isomerism is possible, but for this name we are not considering geometrical isomerism. So therefore option 3 is wrong. Let's come to option 4. In option 4 it is written as 6-formyl. Once again the same issue. If we write 6-formyl, then we would be extending the chain. So let us look at that structure. If we write 6-formyl, then we would be extending the chain 1, 2, 3, 4, 5, 6. At the 6th position we have an aldehyde here in this structure if we write it like this way. So therefore this name is also wrong because this is not the structure given for us, isn't it? So therefore this name is also wrong. Now you might be wondering, then what is the correct name? The correct name is 5-formyl and then 2-methyl hex 3 in oic acid. That is the correct IUPAC name for this molecule because we have the aldehyde at the 5th position, not at the 6th position, isn't it? This is our parent chain and the second functional group should get low number. So that's why we are choosing this parent chain. If we choose this as our parent chain, then we can say that the second functional group is at position 5. We cannot choose this as our parent chain. That is wrong. And by the way, I have seen one more option for this question where it was written as 6-oxo. We cannot call it oxo because we don't have a ketone here. We have an aldehyde. So therefore we have to call it formyl. Of course, option would generate the same structure if we write it this way, but this name is wrong. So like I said, if you write 2,5 dimethyl 6-oxo hex 3 in oic acid, we would get the structure. But the question is, can we call an aldehyde as oxo when it comes as a substituent? No. So therefore this option is wrong. So therefore the correct answer is 5-formyl 2-methyl hexyl-3-enoic acid. That is the correct IUPAC name for this molecule. At the fifth position, we have the formyl. At second position, we have the methyl group. At third position, we have the double bond. So therefore, this is the correct IUPAC name for this structure. Here's a question based on geometrical isomerism. So let's write down the structures in bond line notation. We have 2-methyl pent-2-ene. So pent is the root word. That means we have a 5 carbon chain. 1, 2, 3, 4, 5. At 2 position, we have a double bond, and then at 2 position we have a methyl group. This molecule will not show geometrical isomerism because we have 2 methyl groups on the same side of the double bond. So therefore 1 is incorrect. How about 2? In 2 we have 4-methyl pent-2-ene. That is 1, 2, 3, 4, 5. 2 position we have a double bond. 4 position we have a methyl group. This will show geometrical isomerism because we have a hydrogen here. We have a hydrogen here. Normally in bond line notation we don't show it, but right now I have written the trans isomer, isn't it? So we can also write the cis isomer for this, and that would be this way, where we have hydrogen atoms on the same side. So this is a trans one, this is a cis one as per the old nomenclature. We can also assign EZ notation for this. So if we are following EZ notation for this, then this would be E isomer and this would be Z isomer, because as per Kahn-Ingold-Prelog rules, higher priority comes to carbon. So therefore this is 1, this is 2, on this side of the double bond this is 2, this is 1. So therefore priorities are on the opposite side, therefore E, but here priorities are on the same side, therefore that is Z. Therefore option 2 should be correct. In the case of 3 and 4, we have terminal alkenes. Pent-1-ene, we will have 2 hydrogen atoms on one side of the double bond, isn't it? So let me just write down the structures. 1, 2, 3, 4, 5 pent-1-ene, 4-methyl pent-1-ene. So we have hydrogens here on the same side of the double bond, so therefore geometrical isomerism is not possible. Likewise for 2-methyl pent-1-ene, 1, 2, 3, 4, 5 at 2 position methyl group, so we have 2 hydrogens on the same side of the double bond. So therefore option 2 is correct. The total number of carbon-carbon sigma bonds in mesityle oxide is how many? We know that mesityle oxide is an alpha comma beta unsaturated ketone, which means the degree of unsaturation in this case is equal to 2, because in the carbonyl group we have a pi bond and then alpha comma beta unsaturation, that means that we have a carbon-carbon double bond as well. What is mesityle oxide? 4-methyl pent 3-ene 2-one is mesityle oxide. 4-methyl pent 3-ene 2-one. So let's draw the structure of 4-methyl pent 3-ene 2-one. 1, 2, 3, 4, 5. At 2 position we have the ketone, and then at 3 position we have the double bond, and then at 4th position we have a methyl group. 1, 2, 3, 4, 5. They are asking the carbon-carbon sigma bonds. That would be 5, isn't it? So this is 1, this is 2, and then this is 3, this is 4, this is 5. The carbonyl carbon sigma bond we shouldn't count because they are asking only the carbon carbon sigma bonds. Therefore, the correct answer for this question is 5. Compound with molecular formula C3H6O can show which type of isomerism? In total, 3 different isomerisms are mentioned in the choices. For C3H6O, the degree of unsaturation is equal to 1 plus number of carbon atoms minus number of hydrogen atoms by 2. Oxygen atom doesn't participate in the degree of unsaturation calculation. Therefore, this is equal to 1 plus 3 minus 6 by 2. So, therefore, 4 minus 3 and that is equal to 1, which means a carbon-carbon double bond is possible or a carbonyl group is possible or it can have a ring. So, these are the 3 different possibilities. However, we are not going to consider ring chain isomerism here. Why? Because it is not given in the choices. Ring chain isomerism is indeed possible for this elemental composition, but it is not given in the choices. For example, you can write isomers such as cyclopropanol or 1,3 epoxy propane. They won't become functional group isomerism. They would become ring chain isomerism. Why? Because there is a precedence order when we have multiple number of isomerisms. That is, ring chain isomerism is greater than tautomerism, which is greater than functional group isomerism, and functional group isomerism is greater than metamerism. Metamerism is greater than chain isomerism, and chain isomerism is greater than positional isomerism. This is the order that we should follow. So, therefore, ring chain isomerism is indeed possible here, but that is not given in the choices. Tautomerism is also possible. For example, if you write acetone, then we can consider keto-enol tautomerism of acetone with prop 1-in-2-ol. However, the equilibrium will be 99.99% more towards acetone because acetone is a much more stable compound. Plus, it is not given as one of the choices. So, therefore, let us not worry about ring chain isomerism and tautomerism. And then, how about metamerism? Metamerism is not possible for this elemental composition. So, let us say if you are writing isomer methoxyethene, for example, let us say CH3O and then CH double bond CH2. This fits into C3H6O, isn't it? But if we are comparing these two, we cannot call that as a metamerism. We have to call that as a ring chain isomerism once again. So, therefore, metamerism is not possible. Then, how about positional isomerism? Positional isomerism is possible, but however, because of the precedence rule, we have to consider functional group isomerism in this case. For example, we can also write propanol. In propanol, the functional group is aldehyde. In propane 2-one, that is acetone, the functional group is ketone. So, therefore, we have to consider functional group isomerism as the correct choice here. If you are considering prop 1-in-2-ol and prop 2-in-1-ol, let us write the structures of those two. H2C double bond COH CH3. This is prop 1-in-2-ol, and we can also write prop 2-in-1-ol. These two are positional isomers, definitely, both by OH group as well as the double bond. However, because of the precedence rule, we have to choose functional isomerism as the correct choice in this case. Therefore, option 4 is correct. Which one among the following resonating structures is not correct? We know that conjugation improves the stability of the molecule. So, let us say if we have continuous single and double bonds, then that improves the stability. So conjugation improves the overall stability of the molecule. On the contrary, if we have positive and positive charges or negative and negative charges close to each other, then that creates a repulsive interaction. That would decrease the stability, isn't it? Having positive and negative charges close to each other is okay. That is attractive. But having similar charges, either positive positive or negative negative, that creates a repulsive field. That will not improve the stability of the molecule. So in 3 we see conjugation here, we see a positive charge here and we see a positive charge here, but this is a 1:5 relationship. 2 positive charges are away, isn't it? But in the case of 1, we see 2 positive charges at 1 and 2 position. That is not possible. That would create a strong repulsive field. So therefore 1 should be the correct answer. Having negative and positive charges is okay. Here negative, here positive. So likewise here positive, negative, and then again positive, negative. Here also positive, negative, and then positive, negative. Those things are okay. And here also positive, negative, and then this is positive, this is negative. Those things are okay. That creates attractive interaction. But having 2 positive charges close to each other is not okay. So therefore option 1 should be the correct choice here. The dihedral angle in staggered form of Newman's projection of 1,1,1 trichloroethane is how many degrees? What we have is CCl3 CH3. In the Newman's projection, we draw a circle and then the center point is the front carbon. So let's assume that this is the front carbon and this is the back carbon, or let us put it this way. We have the carbon carbon single bond and then 1 chlorine down, hydrogen up, and then 1 hydrogen away from us, and then 1 hydrogen is towards us. On this side 1 chlorine is towards us and 1 chlorine is away from us. And let's assume that we are looking from here, so to the front, from the front carbon we are looking. So in that case we can put it an Y shape, chlorine chlorine chlorine, and then hydrogen hydrogen hydrogen. Now why we have put like this? Because this dihedral angle is 180 degree, isn't it, between up and down. So if we are taking these 4 atoms, then in the staggered form this dihedral angle is 180 degree. But that's not what they are asking. In the question what they are asking is the dihedral angle among this hydrogen, this carbon and this chlorine. That's what they are asking. So basically this dihedral angle they are asking. That is 60 degree. Therefore 60 degree is the correct answer here. Because if you move another 60 degree, then it would become eclipsed, isn't it? This is staggered form. If you rotate the carbon carbon single bond another 60 degrees, then what will happen? Then we would be having the eclipsed conformer, isn't it? the hydrogen will be here, and here the hydrogen will be here, the hydrogen will be here. So it would be eclipsing. This is the eclipsed form, but they are asking the dihedral angle in the staggered form, and that too these 4 atoms, whatever I have marked in red. The back carbon we cannot see. So this hydrogen, the back carbon, and then the front carbon, and then the chlorine. The dihedral angle among these 4 atoms is what they are asking. So therefore 60 degree is the correct answer. By the way, I have made a short video about what is dihedral angle and why it is necessary when we have 4 atoms or more. Link is given in the description. Please see that if you want to understand what is dihedral angle and why it is necessary for 4 atoms or more. The number of acyclic structural isomers including geometrical isomers for pentene are how many? This question is somewhat deceiving in the sense that they are not asking you to write down the isomers of pentene with only pent as the root word. That is something you need to understand. They are asking you to write down all isomers of C5H10 that are acyclic. At the same time, consider both structural as well as geometrical isomers. This part you need to be clear. We know that the degree of unsaturation for C5H10 is equal to 1. Therefore, number 1 we can write pent 1ene. That is 1 isomer. So 1, 2, 3, 4, 5, and then 1 double bond at position 1. This is pent 1ene. And then number 2 we are going to write pent 2ene, but we are going to write the Z isomer of pent 2ene. That would be 1, 2, 3, 4, 5, and a double bond at second position. We have hydrogens on the same side. What do you call it as the cis isomer? But I prefer the EZ convention because EZ convention is much more superior than cis trans convention, because around the double bond if you have 4 different groups, then cis trans convention will fall apart. So therefore EZ convention is much more preferred. We know that as per Kahn-Ingold-Prelog rules, carbon will get top precedence compared to hydrogen because the atomic number of carbon is higher than hydrogen. So therefore our priorities are on the same side. When the priorities are on the same side, we call it as Z isomer. Therefore the correct IUPAC name for this molecule is in parenthesis 2Z and then pent 2ene. We would write the E isomer now, and that would be 1, 2, 3, 4, 5, and then a double bond at second position. We don't normally show hydrogen atoms in the bond line notation, but I am just showing it here for the sake of clarity. Precedence here is 1, here is 2, here is 2, and then here is 1. Since the priorities are on the opposite side, we call this one as E isomer. So therefore the IUPAC name for this isomer is 2E pent 2ene. Now we are exhausted with the isomers of pentene with pent as the root word. We have to go to butene, isn't it? Because so if we write this way, for example, and put a double bond here, then if we do the numbering from right to left, not left to right, right to left, then that is one and the same as this isomer, isn't it? So therefore we shouldn't do that. That's a redundancy. And then number 4, we are going to write 2-methyl but 1ene. That would be 1, 2, 3, 4, double bond at 1 position and a methyl group at 2 position. Geometrical isomerism is not possible for this because we have 2 hydrogen atoms on the same side. It's a terminal alkene. Therefore, geometrical isomerism is not possible. And the IUPAC name for this molecule is 2-methyl but 1ene. And then number 5, we can also write 3-methyl but 1ene, isn't it? 1, 2, 3, 4, double bond at 1 position, but methyl group at 3 position. 1, 2, 3, 4, and this is 3-methyl but 1ene. Once again, geometrical isomerism is not possible because this is also a terminal alkene. And then number 6, we can write 2-methyl but 2ene. 1, 2, 3, 4, and then a double bond at 2 position, and then a methyl group at 2 position. For this one also, once again, geometrical isomerism is not possible because on the same side of the double bond we have 2 methyl groups. So therefore, geometrical isomerism is not possible. Therefore, the IUPAC name for this molecule is 2-methyl but 2ene, which means that in total 6 isomers are possible. Therefore, the correct answer is 6 for this question. Which of the following molecules does not show stereoisomerism? We have 4 different IUPAC names. Let's first convert them into structures. In number 1, we have 3,4 dimethyl hex 3ene. That would be 1, 2, 3, 4, 5, 6, and then we have a double bond at 3 position, and then 1 methyl group at 3 position, 1 methyl group at 4th position. 1, 2, 3, 4, 5, 6. For this molecule, geometrical isomerism is possible, isn't it? Because we have a ethyl group and methyl group on one side. Likewise, we have a ethyl group and methyl group on other side. So therefore, EZ configuration is possible for 3,4 dimethyl hex 3ene. So therefore, geometrical isomerism possible, optical isomerism not possible because we don't have any chiral centers. How about number 2? Number 2, we have 3-methyl hex 1ene. That would be 1, 2, 3, 4, 5, 6, and then 1 double bond at 1 position, and then 1 methyl group at 3 position. Here we have a chiral center. So this means geometrical isomerism is not possible, but optical isomerism is possible. Why geometrical isomerism is not possible? Because we have 2 hydrogen atoms on the same side of the double bond. It's a terminal alkene. So for terminal alkenes, geometrical isomerism won't be possible. So therefore, we can eliminate that. Therefore, 1 is wrong, 2 is also wrong. Let's work on 3. We have 3-ethyl hex 3ene. That would be 1, 2, 3, 4, 5, 6. We have a double bond at 3 position, and we have a ethyl group at 3 position. Now for this molecule, geometrical isomerism is not possible, isn't it? Because we have 2 ethyl groups on the same side. Therefore, geometrical isomerism is not possible. Plus, we don't have any chiral centers. Therefore, geometrical isomerism no, optical isomerism is also no. This means option 3 is our correct choice here. Let's work on option 4. We have 4-methyl hex 1ene. That would be 1, 2, 3, 4, 5, 6. At 1 position, we have a double bond, and then at 4th position, we have a methyl group. Therefore, we have a chiral center here. So this means geometrical isomerism not possible because it is a terminal alkene, but optical isomerism is possible. Both R and S configurations are possible. For option 2 also R and S configurations are possible. Therefore, option 3 is the only correct choice here. The number of chiral alcohols with molecular formula C4H10O is how many? Assume that stereoisomers as different chiral alcohols. That means if we have a chiral center, then we need to treat them as 2 different alcohols. Now let us first determine degree of unsaturation for this elemental composition. Degree of unsaturation in this case is equal to 1 plus number of carbon atoms minus number of hydrogen atoms by 2. Oxygen atom doesn't participate in the degree of unsaturation calculation. Therefore, this is equal to 1 plus 4 minus 10 by 2. 5 minus 5, that is equal to 0. This means all the alcohol isomers that we are going to write are saturated alcohols. Let us write the isomers one by one. Number 1, we are going to write butane 1-ol, that is CH3, CH2, 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 OH. This is butane 1-ol. We don't have any chiral center. Therefore, let's write isomer 2, that is butane 2-ol. CH3, CH2, CH, OH and then CH3. Now we have a chiral center at position 2, because now we have 4 different groups around this carbon. We have a OH group, we have a methyl group, we have a hydrogen and then we have a ethyl group. Therefore, that carbon atom is chiral. This means that 2 isomers are possible. Both R and S configurations are possible. So, therefore, either it could be 2R butane 2-ol or it could be 2S butane 2-ol. Therefore, we should treat this molecule as 2 different chiral alcohol isomers. Now, we are exhausted with the butane chain because moving this OH group to the third position is not possible. Because if we number it left to right, then that becomes one and the same. Therefore, let's move to propane chain. We are going to write 2-methyl propane 1-ol, that is CH2OH and then CH, CH3 and then CH3. This is 2-methyl propane 1-ol. We don't have any chiral center in this molecule. And then number 4, we can also write 2-methyl propane 2-ol, that is CH3, COH, CH3, CH3. This is 2-methyl propane 2-ol. In this case also, we don't have any chiral centers. Therefore, the correct answer for this question is 2. What is the total number of possible stereoisomers of dimethyl cyclopentane? First of all, this is not a difficult question, but at the same time, if you are not very clear about the concept of meso compounds, enantiomers and the difference between stereoisomers and structural isomers, then there are plenty of opportunities to make a mistake on questions like this. Let me write a structural isomer for dimethyl cyclopentane. The reason I am showing this isomer is because if you are not very clear about the concept of stereoisomerism and structural isomerism, then you would be making a mistake on questions like this. So, this is a structural isomer. This is not a stereoisomer because this molecule is achiral. There is no chiral center in this molecule. Therefore, this shouldn't be included in the count at all. So, let me remove this. Now, we can write 1,2 dimethyl cyclopentane with both the methyl groups up. If we do that, then we are having 2 chiral centers now, isn't it? This is a chiral center. This is also a chiral center. So, therefore, 2 to the power n, we expect 4 isomers. But are we gonna get 4 isomers? No, because this is a meso compound. The molecule has a plane of symmetry. Half of the molecule is a mirror image to the other half. So, what will happen when we have mesomer? We won't get the maximum isomers 4. We will get only 3 isomers, isn't it? Because one of them is a meso compound. This one as well as this one are identical. Whether you put the methyl groups, both the methyl groups up or both the methyl groups down, they are one and the same. Because you can reach to this one if you rotate the molecule 180 degree. Whether you are rotating clockwise or counterclockwise, it doesn't matter. If you rotate 180 degree along the plane of symmetry, then you can get the other one. So, that means both are identical. Both are meso, both are identical. So, therefore, this must be counted as one isomer. This is achiral. I'm just writing it. That doesn't mean that these are two isomers. This is one isomer. Okay, because if you just rotate 180 degree, you can reach to the other one, and we can clearly superimpose both of them. Because half of the molecule is a mirror image to the other half, the net optical activity of meso compound will always be 0. And then we can also get a pair of enantiomers. If you put one methyl group up and one methyl group down, then we can get a pair of enantiomers. So let's say this methyl group is up and then this methyl group is down, and let's assume that this is our mirror plane. Then the mirror image will be like this, and these are non-superimposable mirror images. That means these are enantiomers. So therefore this must be considered as two stereoisomers, enantiomers. Likewise, we can write 1,3 dimethyl cyclopentane with both the methyl groups up. That would once again will become a meso compound, isn't it? If both the methyl groups are up or both the methyl groups are down, they are one and the same, they are identical, and this is a meso compound once again, because once again we have a plane of symmetry. This is the plane of symmetry now. So if you rotate 180 degree, then we can get this one, but that doesn't mean that this is a different isomer. This is one and the same. These two are identical, meso achiral. Now let's put one methyl group up, one methyl group down. So number 5. So if we are writing like this, let's say one methyl group down, one methyl group up for the 1,3 case, then once again we will get a pair of enantiomers. Let's say this is our mirror plane, and then this would be the mirror image. These two are enantiomers because they are non-superimposable, therefore they are enantiomers. So therefore this must be considered as two isomers. So in total we can get 6 isomers. Therefore the correct answer is 6. 2 of them are achiral, 4 of them are chiral. Even though it is achiral, it should still be considered as a stereoisomer. Just because a molecule is achiral having chiral centers, it doesn't mean that it is not a stereoisomer. It is a stereoisomer. Okay, meso compounds are indeed stereoisomers. The net optical activity goes to 0 because half of the molecule is a mirror image to the other half of the molecule. The total number of monobromo derivatives formed by the alkanes with molecular formula C5H12 is how many? We have to exclude the stereoisomers. We know that C5H12 is a completely saturated elemental composition with the degree of unsaturation is equal to 0, because this would fit into the general molecular formula CnH2n plus 2 with the n value equal to 5. Degree of unsaturation in this case is 1 plus number of carbon atoms, that is 5, minus number of hydrogen atoms by 2. So 12 by 2. So 6 minus 6 would be equal to 0. So therefore we don't have to worry about double bonds or rings. And we know that we can write 3 isomers for C5H12. One is pentane or normal pentane, and another is 2-methyl butane. 1, 2, 3, 4, and then one methyl group at second position. And then another isomer is 2,2 dimethyl propane. So these are the 3 isomers that we can write for C5H12. Now at each place we have to remove one hydrogen and put a bromine, because they are saying monobromo derivative, and then see how many structural isomers we are getting. If there is a chiral center, we just have to ignore it. Let's do this one by one. So in this case, let's say we are putting a bromine at position 1. So therefore 1, 2, 3, 4, 5. This is 1 bromopentane, and then we can also write 2 bromopentane. 1, 2, 3, 4, 5, and then 1 bromine at second position. We can also write 3 bromopentane, isn't it? 1, 2, 3, 4, 5, and then 1 bromine at a 3 position. And then let's say if we keep 2-methyl butane as the base, then number 4 we can write 1 bromo 2-methyl butane, isn't it? Because it doesn't matter whether we are putting a bromine here or here, that would be one and the same. So either place if you put a bromine we will get the same isomer. So therefore what we are going to write is 1 bromo 2 methyl butane, 1 2 3 4 and then CH2Br. So in this case the numbering we have to do it from here 1 2 3 4 because as per the alphabetical ordering bromine should come first, and then we can also put bromine exactly where the methyl group is. So that would be 2 bromo 2 methyl butane, 1 2 3 4 1 methyl group and then at the same place bromine. This is 2 bromo 2 methyl butane, and then we can also write 2 bromo 3 methyl butane, that is another isomer, 1 2 3 4 methyl group at 2 position, bromine at 3 position. And then we can also write 1 bromo 3 methyl butane, that is another possibility, 1 2 3 4 and then put the bromine substituent here, keep the methyl group exactly where it was. Now we have to do the numbering from right to left, 1 2 3 4. So this is 1 bromo 3 methyl butane. So these are the 4 structural isomers we can write based on 2 methyl butane as the base, and then using 2,2 dimethyl propane we can write only one isomer, isn't it? Because all of them are methyl groups. So wherever we put the bromine that would be one and the same. So therefore number 8 1 2 3 1 methyl group and then CH2 and then Br, and the numbering has to be done this way 1 2 3. So we have 2 methyl groups at 2 position, 1 bromo substituent at 1 position. So therefore this is 1 bromo 2,2 dimethyl propane. This is the only isomer we can write. So therefore the correct answer is 8 excluding stereoisomers. So therefore 8 is the correct answer. Now imagine what if they had asked the same question saying include the stereoisomers also, then how the answer is gonna change. So we don't have any chiral center in this one, but we do have one chiral center in 2 bromopentane, in 1 bromopentane as well as in 3 bromopentane we don't have any chiral center, but in 2 bromopentane we do have a chiral center. So therefore together it would become 4 isomers based on the pentane, and then let us look at the compounds based on 2 methyl butane. We do have a chiral center here, isn't it? We have a methyl group CH2Br and then there is a hidden hydrogen here and then we have a ethyl group. So therefore this is indeed chiral, and then we do have a chiral center for 2 bromo 3 methyl butane, isn't it? So therefore here it would become 6 isomers. We don't have any chiral center here, so therefore that would count as 1. Therefore 4 plus 6 plus 1 11. So if they had asked include the stereoisomers as well, then the correct answer is 11, but excluding stereoisomers the correct answer is 8. The number of sp3 hybridized carbons in an acyclic neutral compound with molecular formula C4H5N is how many? Now let us first determine the degree of unsaturation for this elemental composition. Degree of unsaturation in this case is equal to 1 plus number of carbon atoms minus number of hydrogen atoms by 2 plus number of nitrogen atoms by 2. So therefore this is equal to 1 plus 4 minus 5 by 2 plus 1 by 2. So therefore this is equal to 5 minus 2.5 plus 0.5, and that is equal to 5 minus 2. Therefore it is 3, which means that we can have 3 pi bonds, isn't it? 3 pi bonds are possible. That could be either 3 double bonds or 1 triple bond and 1 double bond. Both possibilities are there. And the question says we have to draw an acyclic neutral compound. In that we have to find the sp3 hybridized carbons. So let's draw 4 carbons first. 1, 2, 3, 4. Let's make a nitrile group. That would account for 1 triple bond, and then let's put a double bond between. So in this case we can have one sp3 hybridized carbon, isn't it? So we have a sp3 hybridized carbon atom here, and the compound we drew is but 2-ene nitrile. That's what we drew here. 1, 2, 3, 4. We could also draw a compound without the triple bond, like by utilizing 3 double bonds. That would be CH2 and then double bond carbon and then double bond carbon and then double bond carbon and then NH2. In this case we would not have any sp3 hybridized carbon atoms, because the hybridization here is sp2, here it would be sp, here also sp, and then here it would be sp2. But keep it in mind that this would become a basic compound, more basic compared to the other one, and plus we don't have any sp3 hybridized carbons. The structure that we drew here is but 1, 2, 3 triene 1-amine. That's what we drew here. Since the question says neutral compound, we can go with this molecule, and the correct answer is 1. One other structure that we could write is but 3-ene nitrile. That would also have only one sp3 hybridized carbon atom. So whether we write but 2-ene nitrile or but 3-ene nitrile, we are going to have only one sp3 hybridized carbon atom. So this is but 3-ene nitrile. So therefore the correct answer is 1. What is the correct structure of gamma methyl cyclohexane carbaldehyde is? We have the carbaldehyde functional group here. The position that is directly attached to the carbonyl carbon is called alpha, and then this is beta, and then this is gamma. So therefore option A should be correct, that is gamma methyl cyclohexane carbaldehyde. This one alpha beta, this is beta methyl cyclohexane carbaldehyde. We cannot name these ones as carbaldehyde because there is a CH2 group here. So we have to name these ones in terms of complex substituents, like we have to end it as ethanol, basically acetaldehyde, but one of the hydrogens is replaced by cyclohexyl group, but that cyclohexyl group has a methyl substituent. So therefore if you want to write a name for B, then how we can do it? So this is 1, this is 2. So therefore at 2 position we have the cyclohexyl group, but that has a methyl group. So 1, 2, 3. So this means 3 methyl cyclohexyl and then close the bracket and then ethanol. That is the correct way of naming this. How about for D? For D we can name it as, this is 1, this is 2. So 2 and then in parenthesis 2 methyl cyclohexyl and then ethanol. That is the correct way of naming this one. Uracil is a base present in RNA with the following structure. Percentage of nitrogen in uracil is how much? Percentage of nitrogen by mass is equal to total mass of nitrogen in the molecule divided by molar mass of the molecule times 100 because it is percentage composition. Now we need to find out the molar mass. We have how many carbons? 1, 2, 3, 4. 4 carbons are there. So let's find the molecular formula first, C4, and then 4 hydrogens are there because 1, 2, and then 3, 4, and then 2 nitrogens are there, 2 oxygen atoms are there. So therefore 4 times 12, that is equal to 48. That's for carbon. And then for hydrogen, 4 times 1, that is equal to 4. And then for nitrogen, 2 times 14, that is equal to 28. And then for oxygen, 2 times 16, that is equal to 32. So 10 plus 4, 14, 14 plus 8, 22, remaining 2, 2 plus 4, 6, 8, 8 plus 3, 11. So 112. This means percentage of nitrogen is equal to total mass of nitrogen. We have 2 nitrogen atoms. So therefore 28 divided by 112 times 100. So this will be 4 times 7. And then this will be 1 times 7, remaining 4, so 42, so 6 times 7. So basically this is 1 by 4. 1 by 4 means 0.25. So 0.25 times 100, that is equal to 25%. Therefore 25 is the correct answer. Testosterone, which is a steroidal hormone, has the following structure. The total number of asymmetric carbon atoms in testosterone is how many? When we say a carbon atom is asymmetric, if it is connected to 4 different groups, then we can say that that carbon atom is asymmetric carbon or chiral carbon. So instead of finding the asymmetric carbons, let's eliminate all the carbon atoms that are not asymmetric. So we can eliminate sp2 carbons that are part of a carbon-carbon double bond and carbonyl group. So this means we can eliminate this carbon. This is also sp2. This is also sp2. We can also eliminate sp carbons. We don't have triple bond here, but if we do have triple bond in the structure, then you can eliminate those. We can also eliminate sp3 carbons that are part of the methyl group, because here you have 3 hydrogen atoms. So even if the methyl group is attached to something else, in total it becomes 2 different groups, not 4 different groups. So therefore methyl carbon are not asymmetric, so you can eliminate those. You can also eliminate methylene carbons. Here you have 2 hydrogen atoms. So this means even if it is attached to 2 different groups, in total it would become 3 different groups, not 4 different groups. So all the methylene carbons you can eliminate. These are all methylene because this is CH2. So now let us mark those carbon atoms that are left out. 1, 2, 3, 4, 5, 6. These 6 carbon atoms could potentially be chiral. Let us cross check it. We have a hidden hydrogen here, and then we have OH, and then CH2 on this side, and then we have a quaternary carbon. So that means this is indeed asymmetric. We have a methyl group, we have CH2, we have CH, and here also we have CH. But this CH is different from this CH because this CH has a OH functional group. whereas this one doesn't have. So therefore this is indeed asymmetric. How about here? We have a hidden hydrogen once again. We have CH2 on this side, quaternary carbon, and then we have CH here. Therefore this is indeed asymmetric. Here too we have a hidden hydrogen, CH on this side, CH2, and then we have CH here as well. But this CH is different from this CH because this CH is at the intersection between two 6-membered rings, whereas this CH is at the intersection between one 6-membered ring and one 5-membered ring. So therefore there is asymmetry. Therefore this is also asymmetric carbon. How about this one? We have a hidden hydrogen, CH2, CH, and then we have a quaternary carbon. Therefore this is also asymmetric. How about this one? We have a methyl group, CH, CH2, and then this carbon atom is sp2 hybridized because of the carbon-carbon double bond. Therefore we indeed have 4 different groups attached to it. So this means 1, 2, 3, 4, 5, 6. We have 6 asymmetric carbon atoms in testosterone. 0.4 gram of an organic compound gave 0.376 gram of silver bromide in Carrier's method for estimation of bromine. What is the percentage of bromine in the compound X is? We know that number of moles of AgBr is equal to number of moles of bromine. Therefore, number of moles of AgBr is equal to mass divided by molar mass, and that is equal to 0.376 gram, that is given here, divided by molar mass of AgBr is 188 gram per mole. Now mass of bromine is equal to number of moles of bromine times molar mass of bromine. So therefore this is equal to 0.376 divided by 188 times molar mass of bromine is 80 gram per mole. Why we use this? Because number of moles of AgBr is equal to number of moles of bromine. Now if we have to find out the percentage of bromine, then we have to divide this entire expression by the whole compound weight and then multiply by 100. So therefore percentage of bromine is equal to 0.376 times 80 divided by 188 times 0.400, that I am writing it as 400 times 10 to the power minus 3 times 100. 100 divided by 400, so that is 4 times. If I am sending this 10 to the power minus 3 up, then it would be 376 times 80 divided by 188 times 4. So 1 times 4, this will be 20 times 4, and this will be 5 times 4, and this will be 4 times 4, 16, remaining 2, so 28, that will be 7 times 4. 47 times 8 will be 376. So therefore this will be 8. So 8 times 5. Therefore that is equal to 40%. Therefore 40 is the correct answer here. A metal chloride contains 55% chlorine by weight. 100 ml vapors of the metal chloride at STP weigh 0.57 gram. In that case, what is the molecular formula of the metal chloride is? In this problem, we have to find out the number of atoms of chlorine, isn't it? Because valency of chlorine is 1. So that's why everywhere only one metal atom is there. Therefore, we have to figure out the number of chlorine atoms. And we know that percentage composition of an element is equal to total mass of the element divided by molar mass of the compound times 100, isn't it? We don't know what is the molar mass of the compound. Without knowing what is the molar mass of the compound, we can't find out how many atoms of chlorines are there. and we also know that number of moles is equal to mass divided by molar mass, which is equal to volume divided by molar volume, because STP condition is mentioned in this problem. Therefore, we can take the molar volume as 22.4 liter per mole. You can also take 22.71 liter per mole. The final answer won't change. So, if you are taking 22.71 liter, you are assuming that the pressure is 1 bar, temperature remains the same 273 Kelvin. On the contrary, if you are taking this value, then we are assuming that the pressure is 1 atm. So, this is the older definition, this is the new definition. Whichever the value you want to use is your convenience. So, I am going to use 22.4 just to make the math little easier. So, therefore, number of moles is equal to mass given for the metal chloride is 0.57 gram divided by molar mass we need to figure out, and that is equal to volume given is 100 milliliters, which I am writing it as 100 times 10 to the power minus 3 liter divided by 22.4 liter per mole. So, therefore, this will become simply 10 to the power minus 1. So, let us rearrange this equation to find out the molar mass. Therefore, molar mass of the compound is equal to 22.4 times 0.57 divided by 0.1, which we can write it as 22.4 times 5.7, because 0.1 means 1 by 10. So, when that comes up, we are multiplying with it 10. So, therefore, 224 times 57, 7 times 4 28, remaining 2, 7 times 2 14 plus 2 16, remaining 1, 7 times 2 14 plus 1 15, 5 times 4 20, remaining 2, 5 times 2 10 plus 2 12, remaining 1, 5 times 2 10 plus 1 11. So, therefore, 8 6 7 2 1. So, 127.68, that is the molar mass of the compound in gram per mole. So, therefore, percentage composition of chlorine is equal to X times. Why X times? Because we do not know how many chlorine atoms are there. That we have to figure out. X times 35.5 divided by molar mass of the compound 127.68 times 100, isn't it? So, now let us find out the value of X. Percentage composition of chlorine value is given as 55. So, let us write it this way. So, 55 equal to this much. Therefore, 55 times 127.68, I am taking it as 128 divided by 36 times 100. 35.5, I am taking it as 36, and that is equal to X. So, therefore, this is 11 times 5 and 20 times 5 is 100, and we can further divide it. So, this will be 5 times 4 and this will be 3 2. So, 32 times 4 will be 128, and this will be 16 times 2 and this will be 18 times 2, and then this will be 8, this will be 9. So, therefore, 9 times 5, that would be 45. In the numerator we have 11 times 8. So, 11 times 8 will be 88. So, 88 divided by 45, that we need to figure out. So, 88 divided by 45, we can do it one time. So, 45, 8 minus 5 3, 8 minus 4 4, 43. We can't divide. So, therefore, put a 0 and rise it to the decimal. So, now we can do it 9 times. 9 times 45 will be 405. So, therefore, 10 minus 5 5. So, 2 is remaining. So, 25. We once again can't divide. So, put a 0. Now, we can do it 5 times. So, 5 times 45 will be 225, remaining 25. So, this will be keep going. So, 1.9555, which we are approximately going to take it as 2. So, therefore, the X value is 2. This means option 3 is correct. We have 2 chlorine atoms. Therefore, MCl2 is the correct answer here. The correct order for acidity of the following hydroxyl compounds is which one? We have methanol, tertiary butyl alcohol, and then phenol, and then para methoxyphenol and para nitrophenol. Now, in these three cases, resonance effect will be operative because we have the phenyl ring, whereas in these two cases CH3 is there and therefore positive inductive effect will be operative. And we also know that NO2 is a strong electron withdrawing group, whereas methoxy is a electron donating group. So therefore, when we have NO2, this will have negative mesomeric effect. So which means it can pull the electrons away, isn't it? And we also know that when we talk about acidity, we have to see the stability of the corresponding conjugate bases, how stable the conjugate base is. Depending upon that, the acidity of the molecule will be. So obviously once the proton leaves, we will have methoxide in the case of A, and we will have tertiary butoxide in the case of B. Now, between these two, which one will be more stable? Obviously, methoxide will be more stable. Why? Because it is smaller. So therefore, this can be easily solvated. More water molecules can surround this, whereas tertiary butoxide ion is a bulky one, and therefore during solvation the water molecule cannot effectively surround this one. So this means that it will be less stable. Even though inductive effect is there in both the cases, it is the solvation that would decide, and plus the steric hindrance. So therefore, if we are talking about the stability order of conjugate bases, then tertiary butoxide ion will be less stable compared to methoxide ion, which means methanol will be more acidic than tertiary butyl alcohol. This means A has to be greater than B. So therefore 3 is definitely wrong, 4 is also wrong. And when it comes to phenol and phenol derivatives, because electron donating group is there, the corresponding conjugate base will be less stable, because if we want to increase the acidity, we basically have to pull the electrons away, whereas in this case we have lone pair here. So that means that can donate the electron, that is not pulling away the electrons that are here once the proton is left. So which means that the next one should be D. I am talking about the stability order of the conjugate base, and then C, the phenoxide ion, and then E. So we have to see in the reverse way now. So E will be more acidic, obviously, because NO2 is a strong electron withdrawing group. We will have negative mesomeric effect. In these two cases we will have positive mesomeric effect. So which means that option 1 is correct, because E will be more acidic than phenol, and which will be more acidic than paramethoxyphenol. And then we already figured out that A is more acidic than B. So this means option 1 is correct. Here is a question based on general organic chemistry and electrophilic aromatic substitution. We have 4 different molecules. We need to arrange them in terms of order of reactivity in electrophilic aromatic substitution reaction. We have benzene, methylbenzene, chlorobenzene and nitrobenzene. We know that methyl group is an electron donating group with a positive inductive effect, whereas chlorine is an electron withdrawing group with a negative inductive effect. There will be a slight amount of positive mesomeric effect, but the negative inductive effect outweighs the positive mesomeric effect. And we also know that NO2 is a strong electron withdrawing group, and NO2 is a pi acceptor. So keeping these things in mind, let's work on this. So therefore, in nitrobenzene we will have negative mesomeric effect or minus R effect. For this question, we need to think about the stability of the arrhenium complex or the sigma complex during electrophilic aromatic substitution. That's the main thing. So let us look at the resonance structures. If A undergoes electrophilic aromatic substitution, then these are the arrhenium ions we will have. But while B undergoing electrophilic aromatic substitution, we will have positive inductive effect that would stabilize the carbocation, because this is the rate determining step, isn't it? Formation of carbon electrophile bond and the breaking of carbon carbon pi bond, that is the rate determining step, not the breaking of CH bond and formation of CC bond, isn't it? Here it breaks, here this forms, here the CH bond breaks in the next step, but that is not the rate determining step. This is the rate determining step. Simultaneously happening, formation of carbon electrophile bond and breaking of carbon carbon pi bond, that is the rate determining step. So because we have positive inductive effect due to methyl group, the arrhenium ion will be more stable. So therefore the reactivity of B will be very high. Therefore that should come first. Let's look at the arrhenium ions when chlorobenzene undergoes electrophilic aromatic substitution. Here chlorine is an electron withdrawing group and therefore we have negative inductive effect. Therefore compared to methyl benzene, chlorobenzene would be less reactive. Now let's look at nitrobenzene undergoing electrophilic aromatic substitution. When nitrobenzene undergoes electrophilic aromatic substitution, we have to think in two different ways. One is the stability of ortho and para arrhenium ions, and then the substitution happening at the meta position. Obviously the substitution will happen at the meta position, because if it is ortho and para, we would be forming highly unstable arrhenium ions, because we have two positive charges adjacent to each other, isn't it? So not in this structure. So here we have two positive charges adjacent to each other. So here also two positive charges adjacent to each other. So therefore the arrhenium ions would be highly unstable. But the same thing doesn't happen at the meta position. However, we still require harsh conditions for electrophilic aromatic substitution happening at the meta position, like high temperature or strong acids, and therefore the reactivity of D, that is nitrobenzene, will be very less in electrophilic aromatic substitution compared to the other three compounds. So this means B should come first, isn't it? And D should come last. So this means 2 is wrong, 3 is also wrong. But now if we are comparing A and C, then for which one the electrophilic aromatic substitution would be faster, whether it is for benzene or chlorobenzene? Obviously it is for benzene, because in chlorobenzene we have negative inductive effect, not positive inductive effect. So therefore after B it should be A. So this means option 4 is correct. What is the total number of sigma and pi bonds in 2-formyl hexafluorine oic acid? We have a carboxylic acid functional group and the root word is hex. That means the parent chain has 6 carbon atoms. Carboxylic acid gets the top precedence. That's why the number there is not mentioned. And then at 2 position we have an aldehyde, and then at 4 position we have a carbon carbon double bond. Let's put hydrogens to satisfy the valency of carbons. Let us first count the number of sigma bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. We have 19 sigma bonds, and then 1, 2, 3. 3 pi bonds. So therefore 22 is the correct answer. Total number of isomeric compounds including stereoisomers formed by monochlorination of 2-methylbutane is how many? Let us first write the structure of 2-methylbutane. That is CH3, CH, CH3, CH2, CH3. Now, whether we chlorinate one of the hydrogen atoms here or here, they are one and the same, isn't it? So, therefore, number 1, CH2Cl, and then CH, CH3, CH2, CH3. Because this carbon atom has 4 different groups around it, it becomes a chiral center. That means R and S configuration is possible. So therefore we should count it as 2 isomers, isn't it? And then number 3, because we have 2 isomers, I am counting it as number 3. CH3, C, Cl, CH3, CH2, CH3. This is just a structural isomer. What we have is 2-chloro, 2-methylbutane. That is just a structural isomer. And then number 4, let's do the substitution at number 3. So therefore CH3, CH, CH3, and then CH, Cl, CH3. Now this carbon atom becomes chiral because we have a hydrogen, we have a chlorine, we have a methyl group, and then an isopropyl group. So therefore R and S is possible here too. We once again have to count it as 2 isomers. So total 5. And then number 6, CH3, CH, CH3, CH2, CH2Cl. This is just a structural isomer. What we have is 1-chloro, 3-methylbutane. So the correct answer is 6. What is the total number of compounds with chiral carbon atoms from the following is? When we say a carbon atom is chiral carbon atom, if it is connected to 4 different groups, then we say that it is a chiral carbon atom because the mirror images are non-superimposable to each other and we call them as enantiomers. So all we need to look for carbon atoms that has 4 different groups. In this case, we have a hidden hydrogen here. So therefore this is chiral because we have 4 different groups now. Hidden hydrogen, methyl group, and then methylene, and then the carbonyl functional group, the keto group. And then in this molecule, we don't have any chiral carbons. So therefore we shouldn't count that. And then in the third one, the chiral carbon atom is this one because there is a hydrogen and then the nitro group, because if it is written in bracket, it means that it is connected to the carbon. So therefore hydrogen, nitro group, and then the ethyl group we have, and then the carboxylic acid functional group. So we do have 4 different groups around that carbon. So therefore we should count this one also. And then in the fourth one, this one is not chiral because we have 2 ethyl groups. So therefore it cannot be chiral. We have in total 3 different groups, not 4 different groups. And then in the fifth one, this carbon atom is chiral because we have hydrogen and then iodine and then the methyl group and then CH2NO2. So therefore this is chiral. And then in the sixth one, this carbon atom is chiral because hydrogen, alcohol functional group, then the ethyl group, then the CH2OH. So we do have 4 different groups around that carbon. And then in the last one, we have 2 chiral carbons. One is here, another is here. Both of these carbon atoms have 4 different groups around it, because we have a methyl group, and then iodine, and then hydrogen, and then the whole thing can be considered as one group for this carbon. Whereas for this carbon, we have hydrogen and then iodine, and then this whole thing can be considered as one group, and then the ethyl group can be considered as another one. So we do have 4 different groups. So therefore this is also chiral. So this means 5 is the correct answer here, because they are asking the total number of compounds with the chiral carbon atoms, not total number of chiral carbon atoms. So therefore 5 is the correct answer for this. Hello everyone, here is a question based on keto-enol tautomerism. Which of the following has maximum enol content? Keto-enol tautomerism depends upon how many alpha hydrogens are there. We have 3 alpha carbons. The carbon atom that is directly connected to the carbonyl group is called alpha carbon. So here we have 3 alpha carbons. Each alpha carbon has 2 hydrogen atoms. So therefore we have 6 alpha hydrogens, because we have 6 CH bonds. And here we have 2 alpha carbons. Therefore we have 4 alpha hydrogens. In the case of 3 also, we have 3 alpha carbons. Therefore we have 6 alpha hydrogens. In the case of 4, we have 2 alpha carbons. Therefore we have 4 alpha hydrogens. So the correct answer has to be either 1 or 3, considering the maximum number of alpha hydrogens. In the case of 1, what will happen is the enol form would be much more resonance stabilized than the other one. So this is a much more resonance stabilized form compared to what happens here. Because here, let's say we can write the enol form this way, and then we can either write like this if it takes alpha hydrogens from here, or the other form that you can write is either this way or this way if it takes alpha hydrogens from this position. So therefore, which one is more resonance stabilized? This form is more resonance stabilized, and therefore one will have the maximum enol content. Therefore option 1 is correct. The one more form that you can write for 3 is this one. However, we are still going to have only 2 double bonds instead of 3 double bonds. This is sp3 carbon, this is sp3 carbon once again. So at a given point of time, we will have 2 sp3 carbon atoms. But in the case of 1, it is resonance stabilized. Everything becomes sp2 carbon. So therefore 1 is the correct answer here. The sum of sigma and pi bonds in hex 1,3 diene phi ion is how many? Hex is the root word here. So therefore let's draw a 6 carbon chain. Let's number it 1, 2, 3, 4, 5, 6. Now we have a double bond at 1 position, we have a double bond at 3 position, and then we have a triple bond at 5 position. Let's fill the hydrogens in order to satisfy the valency of carbon. So therefore 1 hydrogen at position 6, no hydrogen at position 5, 1 hydrogen each at position 4, 3 as well as 2, and then 2 hydrogens at position 1. Now let's count the pi bonds first. We have one pi bond here, another here, and we have two pi bonds, because triple bond is two pi bonds and one sigma bond. So therefore 4 pi bonds, and then we have how many sigma bonds? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 sigma bonds. Therefore in total it is 15. Therefore 15 is the correct answer for this question. During sulfur estimation, 160 milligram of an organic compound gives 466 milligram of barium sulfate. The percentage of sulfur in the given compound is how much? We know that number of moles of barium sulfate is equal to number of moles of sulfur, because we have only one sulfur atom in barium sulfate. So therefore this is equal to mass of barium sulfate, that is 466 milligram, which I am writing in terms of gram. That's why multiplying with the 10 to the power minus 3, divided by molar mass of barium sulfate. That would be 137 plus 32 plus 4 times 16, that is 64. So 7 plus 2 9, 9 plus 4 13. So 3 remaining 1, it would be once again 13. So 3 remaining 1, so 233 gram per mole. Now to find the percentage of sulfur, we need to find the mass of sulfur. Mass of sulfur is equal to number of moles of sulfur, for which we can substitute this expression. Why we are substituting? Because number of moles of barium sulfate is equal to number of moles of sulfur. So number of moles of sulfur times molar mass of sulfur, that is 32 gram per mole. Now percentage of sulfur is, we have to divide this entire expression by weight of the organic compound, that is 160 milligram, and multiply with the 100. So therefore 466 times 10 to the power minus 3 gram times 32 gram per mole divided by 233 gram per mole times 160 milligram. So 160 times 10 to the power minus 3 gram times 100. So this will be 2 times. 2 times 32 is 64. And then below we have 160. So therefore this is 8 times 8 and this is 20 times 8. So therefore 8 by 20. So this will be 2 times 4, this will be 5 times 4, and then 1 times 5 is 5, and then 100 is 20 times 5. So 2 times 20, 40. So 40% is the correct answer. So therefore 40 is the correct answer here. What is the correct order of stability of the following carbocations? In A we have a tertiary carbocation with 3 phenyl rings, and therefore the charge stabilization will be more because of the resonance effect. Compared to B, A will be much more stable because we have 3 phenyl rings in A, and in B we have only 2 phenyl rings. So we have a secondary carbocation in B. In C we have a secondary carbocation once again with the 2 alpha hydrogens. We have a hydrogen here, and plus it has 6 pi electrons. This means C is aromatic. Therefore much more weightage should be given to C than A, because it obeys the Huckel rule. Because it is aromatic, C is much more stable than A. How about D? D we can only consider hyperconjugation. It is secondary with the 5 alpha hydrogens. Therefore C is more stable than A, and A is more stable than B and D, and B is more stable than D. That's the order it follows. This means that option 4 is correct. Which among the following halides will generate the most stable carbocation in nucleophilic substitution reaction. A carbocation stability is based on combination of factors. It could be hyperconjugation, or it could be resonance, or it could be positive inductive effect, or it could be positive mesomeric effect. But in this case, we need to worry about only hyperconjugation and resonance. Bromine is the leaving group in all the cases. So in presence of a polar protic solvents, once the bromine atom is left after a heterolytic cleavage, in the case of 1, we will get a allylic carbocation, which is primary, has 1 alpha hydrogen, and it is allylic. We have a alpha hydrogen here. In the case of 2, we will get a primary carbocation once again, but it is benzylic. Therefore, it is more stable than allylic carbocation. Primary, no alpha hydrogens, but benzylic. Charge distribution will be much stronger in this case. In the case of 3, we will get a secondary carbocation. It is allylic once again, but it is secondary with 3 alpha hydrogens. We have 1 alpha hydrogen here, we have 2 alpha hydrogens here. Therefore, compared to 1, 3 will be more stable. So, it is allylic. In the case of 4, we will get a tertiary carbocation, but we have 3 phenyl rings. It is benzylic, but with 3 phenyl rings, this will be much more stable than all other carbocations. So, tertiary carbocation, no alpha hydrogens, but it is much more stable because of the resonance effect. Therefore, in terms of carbocation stability order, if we have to arrange it, then 4 first because it is benzylic, and then 2 benzylic once again, and then 3, and then 1. This means that option 4 is correct. That will generate the most stable carbocation. Which one of the carbocations from the following is most stable? We have 4 different carbocations, but all of them are primary carbocations because the carbon atom is directly connected to only one other carbon here. Therefore, all of them are primary and all of them contain only 1 alpha hydrogen. And all the carbocations given are allylic. Therefore, we cannot take a decision based on hyperconjugation and resonance alone. We need to consider additional effects in this case. For example, positive mesomeric effect. Which functional group attached to the allylic unit would stabilize the charge? That's the question here. Even though in the first 2 cases we do see methoxy, there is a CH2 between in the first case. Therefore, it won't be stabilizing the charge as much as the methoxy group does. So, we can write a resonance structure for this in this way that can stabilize the charge. So, CH2 double bond and then CH here and then single bond and then CH here double bond and then oxygen and then CH3, 1 lone pair and then the positive charge. Therefore, we can write a resonance structure that can stabilize the charge for the primary carbocation. How about in the third case? In the third case, the polarization of the carbonyl group is like this. Therefore, if we do write a resonance structure, basically 2 positive charges will be close by, and therefore this won't be stabilizing the carbocation as much as the methoxy does. Fluorine is more like an electron withdrawing group. Even if we write a resonance structure thinking that it can be an electron donating group, then what will happen is we have to put a formal charge, positive formal charge on the most electronegative atom. That's what will happen. So, if we do write a resonance structure like this, CH2 double bond CH and then CH here and then double bond F and then 2 lone pairs, then we have to put a positive formal charge and the most electronegative fluorine atom. Therefore, this is also not stabilizing the charge that is there on the carbocation. Therefore, methoxy group will have a dominant mesomeric effect here, and therefore option 2 is correct here. The possible number of stereoisomers for 5-phenyl pent 4-in-2-ol is how many? Let us first draw the structure of this molecule. Here the root word is pent, that means the parent chain contains 5 carbon atoms. Therefore, 1, 2, 3, 4, 5. At 2 position we have a alcohol functional group, and then at 4 position we have a carbon-carbon double bond, and then at 5 position we have a phenyl substituent. Let us number it 1, 2, 3, 4, 5. We have a chiral center at 2 position. Therefore, this could be R as well as S, but we need to consider geometrical isomerism also here. Therefore, that is another stereo center. So, the number of stereo centers here is equal to 2. We know that number of stereo isomers is equal to 2 to the power n, where n is the value of the number of stereo centers. Therefore, this is 2 to the power 2, therefore, this is 4. Therefore, the correct answer is 4 here. Here the IUPAC name of the compound is given without considering stereoisomerism. But once we draw the molecule like this, let us say OH in this way and then hydrogen behind, then we need to explicitly specify the absolute configuration. How do you name this now? So, we have hydrogen here, as per Kern-Ingold-Prelog rules. If we assign the priorities, then hydrogen will get the least priority, carbon will get the most priority because the atomic number of carbon is higher than the atomic number of hydrogen. So, here our least priorities are on the opposite side. Therefore, this is a E isomer, isn't it? This E could be R and S, and then when we have Z isomer, then that can also have R and S. That is why the answer is 4. So, now let us assign the absolute configuration at 2. The OH will get the top priority. Therefore, that is 1 as per Kern-Ingold-Prelog rules. Hydrogen will get the least priority, that is 4. Here we have a carbon that is attached to 2 hydrogens and then another carbon on the other side. Therefore, this priority should be 2 here, and then here we have a carbon that is attached to 3 hydrogen atoms. Therefore, this should be 3. Let us say we are looking at the molecule from here. We know that the OH is towards us and the hydrogen is behind. In this case, we can put it this way: 1 here, and the methyl group is at the tops, therefore 3 here, and then 4 on the right hand side, so 4 here, and then 2 here. But we cannot determine the absolute configuration this way. We need to bring the least priority group down. Therefore, let us do one swap between these two. If we do that, then 1 here, 4 here, 3 here, 2 here. Let us do another swap, because when we go clockwise or counterclockwise, the numbers has to be in a sequential manner, 1, 2, 3 or 3, 2, 1. It cannot be 1, 3, 2. Therefore, let us do another swap here. 1, 2, 3, 4. Now we can go clockwise, 1, 2, 3. This means this is R. The original should also be R because we have done 2 swaps. Therefore, the correct IUPAC name is 2R and then 4E, then 5-phenyl pent 4-in-2-ol. Instead of alcohol functional group towards us, if hydrogen is towards us, then this will become 2s 4e 5-phenyl pent 4-ene 2-ol. Likewise, we can draw 2r4z and 2s4z. In that case, what we need to do is we need to put both the hydrogen atoms on the same side. Two statements are given and we need to check the validity of both the statements. In statement 1, two structures are given and it is mentioned as isomeric compounds. So what we have here is methyl cyclopentane, whose molecular formula will be C6. We have 8 hydrogens here, 1 hydrogen here, and then methyl group 3 hydrogens, therefore C6H12. How about here? 1, 2, 3, 4, 5, 6. We have hex 3 in. It is in trans position, therefore you can mention it as 3e hex 3 in. If you follow the Kohn-Ingold-Prelog rules, the priorities will come on the opposite side. So this is a trans isomer. And here too we have C6H12 because we have 5 hydrogens here, 5 hydrogens here, and then 2 hydrogens. Therefore, this is also C6H12. That means they are indeed isomers. They could be considered as ring chain isomers. Therefore, statement 1 is correct. How about statement 2? In statement 2, we have two different amines. This is a primary amine and this is a secondary amine because the nitrogen atom here is connected to 2 carbons directly. Therefore, this is a secondary amine. And it is mentioned as functional group isomers. First of all, let us check the molecular formula. So here 1, 2, 3, 4, 5 pentyl chain. So the compound name is pentane 1-amine. On the pentyl chain we will have 11 hydrogens, 5 carbons, so C5, and then on the NH2 group we have 2 hydrogens. Therefore, total number of hydrogens will be 13 and then 1 nitrogen. C5H13N is the molecular formula here. How about here? Here the compound name will be N-ethyl propane 1-amine. That's the compound name. So we have C2H5 here and we have C3H7 here and therefore and then 1 hydrogen here. Therefore, this is also C5H13N. That means the molecular formula is same and they are indeed functional group isomers because one is a primary amine and another is a secondary amine. Therefore, both the statements are correct. That means option 2 is correct. Total number of sigma and pi bonds respectively present in hex 1 in 4-ine are how many? The root word here is hex. Therefore, we have a 6 carbon chain. Let's draw the 6 carbon chain first. 1, 2, 3, 4, 5, 6. We have a double bond at 1 position, triple bond at 4 position. Let's fill the hydrogens to satisfy the valency of carbon. We have 3 hydrogens here. We have 2 hydrogens here. We have 1 hydrogen at 2 position, 2 hydrogens at 1 position. Therefore, we have 8 CH bonds. They are all sigma and it is a 6 carbon open chain. Therefore, it must have 5 carbon-carbon single bonds. They are sigma. Therefore, the total number of sigma bonds are 13. And then we have 1 pi bond here and we have a triple bond here that will have 2 pi bonds. Therefore, we should have 3 pi bonds. Therefore, 13 and 3. Option 1 is correct. Total number of sigma and pi bonds respectively present in hex 1 in 4-ine are how many? The root word here is hex. Therefore, we have a 6 carbon chain. Let's draw the 6 carbon chain first. 1, 2, 3, 4, 5, 6. We have a double bond at 1 position, triple bond at 4 position. Let's fill the hydrogens to satisfy the valency of carbon. We have 3 hydrogens here. We have 2 hydrogens here. We have one hydrogen at 2 position, 2 hydrogens at 1 position. Therefore, we have 8 CH bonds. They are all sigma, and it is a 6 carbon open chain. Therefore, it must have 5 carbon-carbon single bonds. They are sigma. Therefore, the total number of sigma bonds are 13. And then we have one pi bond here, and we have a triple bond here that will have 2 pi bonds. Therefore, we should have 3 pi bonds. Therefore, 13 and 3. Option 1 is correct. Let's find out the number of sp and sp2 hybridized carbon atoms in the given structure. We have a triple bond here, therefore this has to be sp. This is also sp. And then another triple bond here, therefore for this carbon also sp. Therefore we have 3 sp hybridized carbon atoms. How about sp2? We have a double bond here, therefore this is sp2. We have another double bond here, therefore this is sp2. This is also sp2. We have another double bond here, sp2, sp2. Therefore, we have 5 sp2 hybridized carbon atoms. So, 3 sp hybridized carbon atoms and 5 sp2 hybridized carbon atoms. Therefore, option 2 is correct. The alkane from below having 2 secondary hydrogens is which one? What they mean by secondary hydrogens is those hydrogens that are connected to a secondary carbon. For example, let us take a simple case like propane. Here this carbon atom is secondary, this carbon atom is primary, and this carbon atom is also primary. These 2 hydrogens we can consider as secondary hydrogens. Now, why this carbon atom is secondary is because it is directly connected to 2 other carbon atoms, whereas the end carbons are directly connected to only 1 carbon atom, and that is why the end carbons are primary and the middle one is secondary. So, let us just write down the structures and then see how many secondary carbon atoms are there in the first place, then we have to multiply by 2. So, for 4-ethyl 2,4 dimethyl octanes, let me write the structures in bond line notation so that it would be quick. Octane first 1, 2, 3, 4, 5, 6, 7, 8, and then at 3 position 1 methyl group, 4 position 1 methyl group, and then 1 ethyl group at 4 position. Let me number it. Now, this is a secondary carbon, this is a primary carbon, and the carbon atom here, this one is tertiary carbon, this is primary, this is primary, this is also primary, this is a quaternary carbon, the one here, and this is a secondary carbon, this is also secondary, and this one is secondary, this is also secondary, this is primary. So, we have how many secondary carbon atoms? We have 5 secondary carbon atoms in this case. That means we have 10 secondary hydrogens because we had 5 secondary carbon atoms. Therefore, in all those places we have 2 hydrogens. Therefore, this is not the correct answer. Now, number 2, we have 2244 tetramethyl hexane. So, let us write the hexane first 1, 2, 3, 4, 5, 6. At 2 position 2 methyl groups, 4 position 2 methyl groups. Let's number it, and then so this is primary, 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 this is quaternary, this one is secondary, and then this is quaternary carbon again, this is primary, this is primary, this is secondary, and this one is primary. So, we have 2 secondary carbon atoms, and that means we have 4 secondary hydrogens. Therefore, this is also not the correct answer. Number 3, we have 2233 tetramethyl pentane. So, 1, 2, 3, 4, 5, 2 position 2 methyl groups, 3 position 2 methyl groups. Let us number it. We have primary carbon here, here as well as here. We have quaternary carbon here, quaternary carbon here, primary, primary. This position is secondary and this is primary. So we have only one secondary carbon, that means we have two secondary hydrogens here. Therefore, this is the correct answer. Let us work it out for number 4 also. We have heptane, tetramethylheptane, 1, 2, 3, 4, 5, 6, 7 and 2 position 2 methyl groups, 4 position another methyl group, 5 position another methyl group. Let's number it. Primary, primary, primary. This is quaternary carbon. This is secondary. This is tertiary. This is primary. This is primary. This one is tertiary. This is secondary and this is primary. We have 2 secondary carbon atoms. That means we have 4 secondary hydrogens. Therefore, option 3 is the correct choice here. Calculate number of stereoisomers of this molecule. This question was asked in the numerical value type questions and we should find an answer and round it off to the nearest integer. How many stereocenters do we have in this molecule? At the first glance, it would look like we have only one stereocenter, the chiral carbon. However, we need to consider about geometrical isomerism also here. Otherwise, we will be making a mistake here. So, the number of stereocenters here is 2 and the number of isomers or number of stereoisomers is equal to 2 to the power n. Here the n value is equal to 2 and therefore the number of stereoisomers here is 4 isomers, because if we are naming this molecule, how do you name it without considering stereoisomers? You can simply name it as pent 3-ene 2-ol. On the contrary, once you consider the stereoisomerism for the chiral carbon, then it will be R and S. But then you have to consider geometrical isomerism, cis and trans also here. Or you would like to, you can call it as E and Z. So 3E and 3Z also. This 3E will have R and S and this 3Z also will have R and S. And that's why it is 4. Therefore, 4 isomers is the correct answer here. Let me put it this way. Let us draw the isomer this way. So, CH3, C double bond C, hydrogen on this side and then hydrogen on the other side. Then we have a chiral carbon and then OH and then the hydrogen is behind and then we have a methyl group. So, if we are assigning RS notation for this particular carbon, then we can put it this way. So, the OH is on the left hand side, so that is first priority. Hydrogen will get the least priority as per the Kahn-Ingold-Prelog rules, and then this methyl group will get the third priority, and then this is carbon connected to hydrogen but also connected to carbon and double bond, and therefore that should get second priority. So, if we do a swap between 3 and 4, then 4 comes down, 3 goes here, 1, 2, 3. This is clockwise, this is R and therefore the original is S, isn't it? And therefore 2S and then this is higher priority, this is lower priority, this is lower priority, this is higher priority as per the Kahn-Ingold-Prelog rules. So, our priorities are on the opposite side. This means it is E isomer. Therefore, 2S, 3E, pent, because we have 5 carbon atoms in the parent chain, 3-ene 2-ol. That should be the correct IUPAC name. Now, we can also get 2R3E, pent 3-ene 2-ol, once we consider that the OH is behind us and the hydrogen is towards us and then the methyl group here and then whatever the rest here. On the contrary, once you put both the hydrogen atoms on the same side, then we can get 3Z 2R, that is another isomer. We can also get 2S 3Z pent 3-ene 2-ol. That's why 4 isomers here. thyroxine, the hormone, has the following structure. What is the percentage of iodine in thyroxine is? We need to find out the nearest integer. In this case, percentage of iodine is equal to total weight of iodine divided by total weight of the compound times 100. First of all, we need to figure out the molecular formula of the compound so that we can find out the molar mass of the compound. So, benzene ring has 6 carbons. We have 2 benzene rings. So, C12 and then 13, 14, 15. So, we have 15 carbon atoms. We have how many hydrogen atoms? We have 1 here and then 2 and then 3, 4, 5. We have 2 hydrogen atoms here, 7. We have 2 hydrogen atoms here, 9. There is one more hydrogen atom here, 10. There is one hydrogen atom here. So 11. We have 11 hydrogen atoms. We have 4 oxygen atoms. We have 1 nitrogen atom and we have 4 iodine atoms. So that is the molecular formula. Let's figure out the molar mass. Therefore, 15 times 12, that is 180. And then next, hydrogen, we have 11 of them. So 11 times 1, 11. And then oxygen, we have 4 of them times 16, and that is equal to 64. And then nitrogen, there is 1 nitrogen, so 1 times 14, so therefore 14. And then iodine, we have 4 of them, 4 times 127, and that is equal to 508. So therefore this total is 8 plus 4 12, 12 plus 4 16, plus 1 17, remaining 1. So 8 plus 1 9, 9 plus 1 10, and plus 7, so 17. Once again remaining 1. So we have 5 plus 2, so 777. That's the molecular weight. So therefore molecular weight is 777. Therefore percentage of iodine is equal to 508 divided by 777 times 100. To make the math easier, I am writing it as 500 divided by 750 times 100. So which is like 2 by 3. So 2 by 3 is 66.66. So since I have reduced the denominator more, I am taking it as 65. So 65% is the correct answer. So therefore 65%. So if you calculate the exact value for this, you will get somewhere around 65.37. So 65 is the nearest integer. Therefore 65% is the correct answer for this. Here is a question based on percentage mass composition. An organic compound weighing 500 mg produce 220 mg of CO2 on complete combustion. What is the percentage composition of carbon in the compound is? We have to find out the nearest integer. We know that mass percent or percentage composition of an element is equal to mass of element in 1 mole divided by molar mass of the compound times 100. And therefore, what is the mass of element in 1 mole for carbon? Molar mass of CO2 is 44 gram per mole, isn't it? Because it is 12 plus 2 times 16. So that is the molar mass of CO2. So in 44 gram per mole, how much carbon is there? 12 gram. So 12 by 44. Therefore this means here we have to multiply this with 220 milligram. So that's our mass of element in 1 mole. So therefore this is equal to 12 by 44 times 220 milligram divided by molar mass of the whole compound, that is 500 milligram times 100, milligram we can cancel, 20 we can cancel, this is 1 times 5, this is 4 times 5 will be 20, so 4 remaining 2, so 20 once again, so once again 4 times 5, so 44 we can cancel, therefore this is 12%, therefore 12 is the correct answer here. Identify the correct statements from the following. In option A, we could see pentane 3 bond and pentane 2 bond, and it is written that they are metamers. Metamers are isomers where they should have the same molecular formula. Let's check that. Do we have same molecular formula? In both the cases it is C5H10O, and different alkyl groups should be substituted over a functional group. So we do see that. We have a propyl group and methyl group in pentane 2-1, and we have 2 ethyl groups in pentane 3-1. So therefore they are indeed metamers. Some of you might get a doubt whether they are position isomers or not. Remember the priority order. Ring chain isomerism, then tautomers, then functional group isomerism, then metamers, then chain isomerism, then position isomerism. Therefore, metamers comes much before position isomerism. So this means they are indeed metamers. So A is correct. How about B? In B we have butane nitrile. So what we have here is butane nitrile and 1 isocyanopropane. So these are the 2 isomers given, and the molecular formula is same. For both of them it is C4H7N. We have cyano functional group, that is nitrile, and then isocyano functional group. So therefore they are indeed functional group isomers. So B is also correct. How about C? In C we could see butane 1-ol and pentane 2-ol. Are they position isomers? No, because first of all they are not isomers itself, because the molecular formula is not same. In one case the molecular formula is C4H10O. In another case the molecular formula is C5H12O, and therefore they are not isomers at all. And then in option D we have butane 1-amine and N-ethyl propane 1-amine. Now the molecular formula for butane 1-amine is C4H11N, and the molecular formula for N-ethyl propane 1-amine is C5H13N. Are they homologous? To be considered as homologous, the functional group has to be same. In this case, the functional groups are not same. In butane 1-amine, the functional group is a primary amine. The NH2 is directly attached to only one carbon, whereas N-ethyl propane 1-amine is a secondary amine, and therefore we can't say that they are homologous. Here the NH is attached to 2 different carbons, so therefore it is a secondary amine. Therefore D is also wrong. This means option 2 is correct. In 3,3 dimethyl hex 1-ene 4-ine, how many sp3, sp2 and sp hybridized carbon atoms are there? Let us draw the structure first. The root word is hex here. That means the parent chain has 6 carbon atoms. So 1, 2, 3, 4, 5, 6. At position 3 we have 2 methyl groups. Therefore CH3, CH3. At position 1 we have a carbon-carbon double bond. At position 4 we have a triple bond. Let's fill hydrogen at remaining positions so that we can satisfy the valency of carbon. Now let's figure out the hybridization. At position 1 it is sp2 because we have a double bond. Position 2 also it is sp2. Position 3 it is sp3 because we have 4 carbon-carbon single bonds. Even for the methyl groups it is sp3 because we have 4 single bonds, 3 carbon hydrogen bonds and 1 carbon-carbon bond. So therefore for the methyl groups also it is sp3. Position 4 as well as 5 because of the triple bond, the hybridization is sp, and then at position 6 it is sp3 once again. So how many sp3 are there? 1, 2, 3, 4. They said carbon atoms, and therefore we have to include the methyl groups also. So that means we have 4 sp3, and then how about sp2? We have 2 sp2 carbons, and we have 2 sp carbons. This means option 2 is the correct choice here.